All right, recording is rolling. All right, you guys are back from lunch, so I'm gonna fill you in on details of these last few slides that I didn't get to before. So quantum mechanics. Now, I've covered some quantum mechanics with you guys. This is the slide we ended on. We're talking about Schrodinger's cat, or this is just complete hypothetical thought experiment. It's something you can't really do, sort of by the nature of it. But that's the last one I saw. What are some other details about quantum mechanics? There's this really weird one called quantum entanglement. Now, this involves, so the basic premise is if you start with a pair of entangled particles, right? So one thing that you guys have learned is that there are certain conservation principles in the universe, like conservation of energy, conservation of momentum. One of them is conservation of angular momentum. You guys remember, like, if an ice skater spinning, pull their arms in, they spin faster, right? So conservation of angular momentum. Now that also applies down at the atomic scale. So say you have a pair of entangled particles where the sum of the angular momentum would be zero. You separate out those particles. Well, if one of them has, let's say, like a clockwise angular momentum, the other one must have a counterclockwise angular momentum, right? So it's not exactly like that, but just to kind of simplify a little bit, has to be one or the other. But since we're talking about quantum mechanics, remember that in quantum mechanics, things don't exist definitively like in Newtonian mechanics, where you can like point at, say, an object and say, that's a point mass. I can tell you exactly its position, its velocity, blah, blah, blah. No, things exist instead, down at the atomic scale, things exist probabilistically. And that also includes, weirdly enough, things like angular momentum. Right. Now, angular momentum is still conserved, right? So the sum of angular momentum between these two particles would still be zero, but neither of them has a well-defined spin until you measure it. But here's the thing: like, once you measure the spin of one particle, it does become defined, and therefore the other one must have the opposite spin. Okay, so maybe that's okay so far. Right. Here's the thing: if you separate out these two entangled particles at some distance, let's say, just for sake of argument, like 1 light year. Now, of course, that's never actually been done at that distance, but just to run with the numbers, 1 light year. And you measure the spin of one particle. Well, remember that there's this limiting speed of light in the universe. So based on general relativity, or just relativity in general, you would think, okay, well, it would take 1 year for that information to travel to the other particle so that it could define that other particle as having the opposite spin, right? Something like that, right? There would be a certain time delay. But that's not actually what happens. The other particle instantaneously adopts the other spin. All right, so you measure, so they both start off with undefined spins. You measure one, and immediately, faster than the speed of light, sort of the information carries over and defines the other. Now, that seems really weird, but Einstein's interpretation of this was, well, maybe these particles have some kind of like hidden information where we can't really determine what the spin is, but it's sort of already baked into the cake all along, right? And just when we measure one, then it becomes revealed. So of course the other one would have the opposite because it would have to, right? But that was actually, that idea was debunked with this experiment in 1964 by a guy named John Bell. I think I mentioned a YouTube channel called Veritasium. He does a really good explanation of this. Now, it's a pretty long video, some like 10, 15 minutes long. You have to watch it like a few times. You have to think really, really deeply about how this would work out. But he shows that that's actually not the case, that these particles would have hidden information, which would have been really nice in terms of like Einstein mechanics to be able to explain this all away, right? But there is some phenomenon where, yeah, they start off with undefined spins. You measure the spin of one, it becomes definitive, and immediately, faster than the speed of light, the other one adopts the opposite spin, right? Now, there's maybe one last thing onto this, which you think, well, okay, if there's something that's breaking the speed of light, if we could somehow maybe turn this into useful information, we could maybe like send emails faster than the speed of light, right? So somebody could be based on Mars, where maybe it would take like a few minutes for a message to reach them, but could you like send an email that would reach them instantaneously, and now you have faster than light communication. And that, though, everybody seems to say, no, that's not going to be the case because this information is random. So it's not non-random information. You can't like embed information into it other than just the random spins of these things. So this is a really weird one. This is one of those weird sort of exceptions to this limiting speed of light in the universe. Maybe hits at some things that we don't fully understand about physics, but yeah, that's a real weird one there. Right? Oh, and this phrase at the bottom, spooky action at a distance. That was Einstein's phrase for this, what's called quantum entanglement. All right, standard model. Ooh. maybe I should have organized this a little bit different. Anyway, all right. So if you ask a chemist what are the basic building blocks of matter, they'll point to the periodic table. They say, okay, well, everything you see, all the ordinary matter is made of something or some combination of things in that periodic table, has 100-ish elements in it, right? They're organized by different properties, right? Different chemical properties, right? But then if you think about it, say, oh, hold on a minute. All those elements can really be broken down into protons, neutrons, and electrons. So maybe that's more fundamental. Maybe it's just those three things. Well, anyway, you go talk to a particle physicist and say, yeah, actually, you're headed in the right direction. And they'll throw this at you, right? This what's called the standard model. I mean, this looks kind of like a periodic table, sort of, right? I'll say there are these 17 elementary particles. Well, really, it's like these 12 fermions on the left, and then these 5 force carriers, called bosons on the right. Right. So one of them is the electron, right? You see electron right here, right? That is considered fundamental. Like you can't break that down into anything more fundamental. Another one's a photon, right? It's one of these bosons, right? This is the carrier of the electromagnetic force. The gluon is the responsible for what's called the strong force, holds the nucleus together. Like otherwise, why would all the protons hang around in the nucleus? That doesn't make any sense from electromagnetic point of view, right? So talking about gluons, right? There's these W and Z bosons. Okay. What you don't see on the standard model are anything about protons or neutrons. Wait, I thought protons and neutrons were some of these basic building blocks. Right? Well, not exactly, because those can be broken down into up and down quarks. I think it's like 2 ups and a down make a proton, and 2 downs and an up make a neutron. Right? So some version of that, right? And there are these other elementary particles too, right? So they're kind of like charm and top and strange, right? And you can combine those, make different kinds of particles, right? But yeah, so talk to a particle physicist, and they'll tell you that this right here is these are the basic building blocks of everything. Now, there's a mystery as to why exactly it's this. Like, why are there exactly like these 17 elementary particles? Like, why not any other number? Right? Why is this not organized any differently? So there's still a lot of open questions, but this has been uncovered empirically by smashing atoms together at mostly the Large Hadron Collider. But come back to that idea. Right, so there have been these 4 identified fundamental forces in the universe. Right? So most physics textbooks, you open it up and say, okay, there's 4 fundamental forces. And in this class, AP Physics, we really only cared about the top 2. Right? So we got this gravitational attraction, right? Masses gravitationally attract, and electromagnetism counts for almost everything else. So electricity and magnetism, obviously, it's like baked into the name, but really anything to do with chemistry, right? We're talking about interactions of what like valence electrons, that's electromagnetic, right? But really all contact forces. So if you push or pull on something in physics, sometimes we call something a normal force. You set something on a table, there's a normal force holding it up. Right. Or how about friction force, right? All those fall under the umbrella of electromagnetism because they all involve something to do with like electrons pushing against electrons some way or another. Right? So really these top 2 are like the only ones we talked about in this class. Now, going to like higher level physics classes, like graduate level, you start to get into, let's say these bottom 2, the 2 nuclear forces. It's called strong nuclear force and weak nuclear force. Maybe not super creatively named, but there you go, pretty descriptive. And so strong nuclear force, this is what holds the nucleus together, right? Why would all the protons and neutrons hang out together? Well, I guess this is the explanation for that. The weak nuclear force is related to radioactive decay. Now, not all atoms are radioactive, but some are, right? Like some isotopes of uranium, carbon-14, which talk about too, right? So there you go. There's these 4 fundamental forces. Right. Now that I gave you guys that description, let me go back and edit this a little bit. So there's a really good case to be made. Now, this is a really weird one. I'm going to refer to that channel, Veritasium. Again, also, he has a really good explanation of this, that gravity is technically not a force. But what gravity actually is instead, from a general relativity point of view, is an artifact of the warping of space-time, right? And it maybe just kind of simplify this a bit, because from a Newtonian point of view, okay, masses gravitationally attract, like everything I taught you in AP physics, you'd set up orbits, blah, 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 right? It makes sense to call it a force, right? But Einstein starts thinking about this and says, well, hold on a minute. I know, for example, here, let's just think horizontal forces. Suppose you're like sitting in a wagon and somebody pulls the wagon, right? Or you're sitting in a plane and the plane starts to take off, or you're sitting in a car and the car starts to drive forward, right? And the seat pushes against you. You can feel that force, right? You feel that force. You feel a change in motion. You feel that acceleration, right? And maybe quantify like so many Gs, right? Like 10 meters per second squared would be like 1 G, right? Something like that. 20 meters per second squared, you feel 2 Gs. You can feel that force, right? But what about like sitting in this room? Well, all of us right now feel like 1G on us, but really the force from a Einstein point of view is the normal force of the floor pushing up on you, or like the desk that you're sitting on is pushing you up, right? But if you were to say like jump off a ledge or jump off a building, right, and like go into free fall, what would that actually feel like? And you would feel like an astronaut, right? Like you see those astronauts floating around in space, International Space Station. They feel like there's no gravity, although they're in a gravity field. They're just like falling around the curvature of the Earth, right? But that's different from like being in a car being accelerated, or like being in a plane, or right. Again, like being accelerated, or sitting in a wagon and somebody's like pulling the wagon, right? You don't feel that force. You actually feel like you're in free fall. You feel an absence of force. So maybe this is like a different type phenomenon. Again, this is what Einstein figured out, which is really weird, because this was before space travel, but Einstein was able to figure that out before space travel, right before, just a few decades before, right? So what's actually going on, as he says, that space and time are part of one four-dimensional fabric. And right now, the fact that we're all like, we feel at rest, right? We're saying, hey, well, inertial frame of reference, I'm not moving, right? From Newtonian point of view, it says, well, actually, there's a normal force that's pushing you up, and that's accelerating you not through space, but through time, right? So think of it sort of analogous to like a centripetal force, like that, right? Like there can be a net force on you, but you don't actually like change your radius of curvature compared to like what you're orbiting, right? So yeah, so is gravity technically one of these four fundamental forces? Does it really fit in with these other three? Well, there's a good case you can make that that's not the case. This is also true, like this whole standard model I told you guys about, gravity doesn't actually fit in with anywhere in the standard model. Like all these bosons are responsible for like these other forces, right? The weak and strong nuclear forces and the electromagnetic force in the case of the photon, right? But gravity doesn't actually fit anywhere in the standard model. So how do you combine these different parts of physics? This is one of the big open questions, like one of the big unknowns. Yeah, is there's this whole quantum mechanics to describe anything atomic scale, and then you have general relativity to give like maybe like a broader picture of what you guys learned as Newtonian universal gravitation, right? But is there some kind of overall theory, like unifying theory, that could explain like both of these parts that seem to in some ways to contradict each other, have conflicts, which would, like if there was some kind of unification theory that could explain both general relativity and quantum mechanics simultaneously, then there would be a better understanding of maybe what's going on inside black holes, or what was going on at the point of the Big Bang. Those are like extreme questions where these different theories come into conflict with each other, right? And the other way I want to edit this is like the screen you guys are looking at. I did read a science article about a year ago, I want to say something like that, where there were some experiments being done at a particle collider. I want to say it was one of the states, I think maybe Fermilab, where there was some like tiny deviation in the motion of particles, again, consistently and statistically, that was not exactly consistent with these forces on the screen. So is it possible that there's a fifth very weak force that has some tiny influence somewhere else? That could be the case too. That's what that article at least seemed to imply. Right. But anyway, most physics textbooks you open, you'll be given this list of these four fundamental forces that are driving everything in the universe. Okay. Right. Let's think about that weak force. And one application of this is something called radiometric dating. Right. Sometimes carbon dating, for example. Okay. So again, not all atoms are radioactive, but some are. One I'm going to use as an example is carbon-14. Now, most carbon is carbon-12, has 6 protons and 6 neutrons, right? All of us right now have a bunch of carbon in us, right? And the vast majority of it's like carbon-12. It's like 99.9 something percent is like carbon-12, right? But there's a small percentage of carbon that's these other isotopes. One of them is carbon-14. Given enough time, carbon-14 will decay into nitrogen. Okay, so, right? And all of us right now have a small proportion of carbon-14 in us. In fact, it's about the same proportion in all of us. And that's true for all living matter. All organic matter has a small proportion of carbon-14. Again, tiny, but it's there, right? Now, you wait 5,700 something years, and half of that carbon-14 will decay into nitrogen. Wait another 5,700 years, and then half of that, and then half of that, and then half of that, and so on, right? So you could say that carbon-14 has a half-life of 5,730 years, right? what a half-life is, right? And if you put on a graph the amount of, say, some radioactive substance you have as a function of time, then it will create this exponential curve. This is an exponential decay curve. And one way you can describe the exponential decay curve is like with this yellow box here. You know what, I should have put it on here. There's also another version I've seen, which is the amount is equal to the initial amount times 1/2 to the power of the number of half-lives that have passed, right? Which is maybe more intuitive, but the one that I actually listed up here is like the more like strictly mathematical way, right? And that E, you guys know E is like the 2.71828 irrational number, right? So that's nice for a number of reasons. You might, if you're in calculus, you know that the rate change of E to the X is E to the X, right? That's one thing that makes E nice, right? And it's a negative exponent because it's exponential decay, right? So here, you start off with some amount, right? You wait one half-life, and now you have half of what you started with. Wait another half-life, now you're down to a quarter. Another half-life, now you're down to an eighth, right? And this could continue indefinitely. Now there's a little bit of plus or minus, right? So this becomes inaccurate after like so many half-lives, but to give you an idea, right? Well, suppose you're an archaeologist, you go out and you dig up some ruin, right? You dig up some old mammoth, right? And you say, oh, I wonder how old this mammoth is. And you carbon date it, and it comes out to have about a quarter of the carbon-14 that it should have had it been alive or like died yesterday, right? A quarter. Okay, so it has a quarter of what it started with, right? Do a little bit of math, say, okay, well, 2 half-lives have passed. And since we know the half-life of carbon-14, see, 2 of that's about 11,000 years. Wow, this mammoth is about 11,000 years old, right? So that's how you do carbon dating. Right? Now, that's just carbon-14 as an example, but you could do that with anything that's radioactive and like lasts long enough. So another famous example is how was our solar system or our planet dated? Did you guys know how old our planet is considered to be, like the textbook value? Okay. It's about 4.5 billion years, about 4.5 billion years, right? Well, how do they know that? How do they know 4.5 billion years, right? So the main method involves looking at rocks that have uranium and lead in them. Now, uranium is radioactive. It goes through the whole decay process. It goes through like a whole chain of like other elements decays into that are also radioactive. And that continues and continues until finally it reaches lead. And lead is not radioactive, so it's stable. So if you have a fresh piece of uranium, then it might be like all uranium. And if you have a very, very old piece of uranium, then you'll get a higher proportion of lead. And since scientists can in a lab calculate or like measure the half-lives of like this whole process, right? They can know if they know the proportion of lead to uranium inside some very old rock, they can date like how old that rock is. And the oldest rocks that have been found on Earth consistently are 4.5 billion years old. So it's thought that, now, of course, nobody knows, nobody was around 4.5 billion years ago, but the leading thoughts, the leading ideas are that either our sun used to be a larger star and like went nova or supernova like 4.5 billion years ago, and then our solar system is like the remnants of that. Or there's some similar ideas that maybe aren't exactly that, but kind of similar to that. Right. So our sun might be like a second or third generation star itself. Right. It's had like past lives where it was larger, and then all the elements basically larger than helium are usually created with that method, with a star going nova or supernova at the end of its life cycle. And every solar system will have a unique, sometimes it's called a fingerprint of elements that go along with it. So the mix of like the ratios of, let's say, like just to pick two, I don't know, iron to carbon on Earth are similar to what they are like on Mars or like some asteroid or anywhere within our solar system. And that's all evidence that they were all created at the same time about 4.5 billion years ago. Okay. And our like natural elements only go up to number 92, which is uranium. The atomic number 92 is uranium. Right now, there are elements beyond that. Right, one of them is plutonium. And is there plutonium on Earth? Yes, but only since 1945. So all the plutonium in the world has been created artificially. It was never around to start with. Now, is it possible that other solar systems had like larger supernova explosions and naturally have plutonium? Yeah, that's almost certainly the case. In fact, there might be like even larger elements that are naturally existing in other parts of the galaxy that we just like haven't come across because they just don't exist on Earth, because naturally ours only go up to number 92 uranium, right? Fusion and fission. Right, so if you look at the binding energy per nucleon, and a nucleon could be a neutron or a proton, right? There's also an upside down version of this graph that mass per nucleon basically mirrors it. It's the same idea, right? The mass per nucleon actually depends on what atom you're in. And the binding energy per nucleon, well, it's just the upside down version of that. So if you change from one element to another element, which is a nuclear process, remember, this is not a traditional chemical process. This is nothing you did in chemistry, unless you talk about nuclear physics, which you probably didn't, right? The mass per nucleon and the binding energy per nucleon changes. And that difference in energy is given by E equals mc squared. So if you know the difference in mass, right, that's the M, right, the difference in mass, E equals mc squared, you can calculate the E energy, and C is the speed of light, that's being squared. We're talking about an enormous amount of energy. So there's two ways you can go on this to get energy, to extract energy from a nuclear process. One is that you can start with a heavy atom like uranium. One isotope of uranium is this one right here, U-235. That's the one that's most useful for nuclear reactions. You bombard that with a neutron. This is the most common reaction you'll get out of that. It'll break into krypton and barium and release like a bunch of energy. Right? So you go from about here on this graph to like somewhere up here. And there's a height change. It's a small height change. Well, at least on this graph, right? But that's an enormous amount of energy. About 20% of the energy running everything in this room right now, the air conditioning, the lights, the projection, computers, when you guys charge your cell phones, about 20% of that is comes from, well, some fission reaction, right? All the nuclear plants we have in the world right now are all fission reaction plants. So they involve like breaking apart heavy atoms like uranium into smaller atoms and releases like a ton of energy. Okay. Okay. Now, the other way you could go with this is you could go from hydrogen to helium. Well, that's the most common way to do what's called fusion. Right? So you can fuse together two small atoms and release an even more enormous amount of energy. This is almost 1,000 times the energy that you get from a fission process. Now, these isotopes of hydrogen here, shown here, are not traditional hydrogen. Traditional hydrogen is just like one proton and one electron, right? Here I'm showing deuterium, which is proton neutron, and tritium, which is proton and two neutrons, right? So this, again, this is just one reaction you could do, but you get like almost 1,000 times the energy here than you do compared to here. Okay, now we can make hydrogen bombs, but we haven't been able to exactly commercialize this process for the electric grid. But we're getting close. There's breakthroughs all the time, and there's a lot of hope right now that artificial intelligence will be able to carry us over the line and finish this problem for us. And this this fuel right here, these different isotopes of hydrogen supposedly are really abundant in just the oceans. So like once this problem becomes cracked, then like fossil fuels won't be a problem anymore. We'll be able to just pretty much run everything on fusion, and it'll pretty well solve all our problems. Right now, where this graph comes together in the middle is iron. So if you start off with iron, you can't really extract energy from that, right? Because fusion leads up to iron, and then fission breaks apart down to iron. Right, Feynman diagram. So these all these particle reactions at Large Hadron Collider, they're messy reactions, and they get lots of different particles that come out of these. So this is one example of a diagram that can show particle interactions. Now, traditionally, time is shown on the vertical axis and then space on the horizontal, kind of opposite what we usually do in this class. So here I'm showing like two electrons interacting. We got a photon released, and then, ooh, see these like backwards arrows? They're showing like backwards to time. That just means it's an antiparticle, and in this case, what's called a positron, right? So positrons are like electrons; they just have like negative mass and negative charge and like negative thing, right? And so that's just one example of Feynman diagram. All right, a little bit of statistics. How many guys took stats, or how many guys took stats? Ooh, really? Just one? Just one? Okay. All right. So tell you guys a little bit about stats. This is one of these. I mean, there have been a number of classes I've taken in my life that really like changed my view of the world. I mean, like one is physics for sure, and one of these is statistics. So let me tell you guys a little bit about statistics. So what you guys are looking at is called a normal distribution, right? Normal distribution curve. Now, not all data is normally distributed, but a lot of it is, or can be approximated by something that is, right? So to guys, basically how this works. One activity I like to do with students usually is have students measure their heights, right? So they measure their own height in centimeters, and they measure the heights of all their friends in centimeters. Then you can plot them. So maybe you have like, oh, are you like, make up something crazy? I don't know, like 160 centimeters, then 170 centimeters, 180, 190, 200 centimeters, right? And then you can start making bar charts, because like who's this tall, who's this tall, who's this tall, right? And it starts to make like a normal distribution type graph, right? Now, is height exactly normally distributed? No, I'm simplifying a little bit, but you guys get the idea, right? Right. And even if you just have a handful of people, you can run some stats and figure out, get a pretty good idea of what this curve is going to look like. I should have put a couple of other formulas up here. So one is just how to find the mean average, here represented with mu. And you guys know how to find the mean, right? You just add up all the numbers and divide by the number that are there, right? And then a little bit more abstract idea is something called standard deviation. I should have put the formula on here because I really like this a lot, but it measures the spread of information. Do you guys see right here at the 1 sigma, there's like an inflection point? See how like the middle of this graph is like an upside down bowl, and the tails of the graph are like right side up bowl, right? There's a change in concavity. You guys see that change in concavity, right? So there's an inflection point right here at the one standard deviation from the mean, right? Now, let me compare two populations to give you an idea of what this spread, like how spread out this curve could be, what that idea would mean. Let's say you're comparing the heights of people to the heights of dogs, right? Now, one obvious difference would just be the mean. Like the average person is taller than the average dog. Like if I put another curve on here to represent dog heights, and this curve already shown is people heights, the average dog height is going to be like somewhere down here, like peak somewhere down here. Would that be true? Right? It's going to be a shorter height, right? But now think about like the spread out of the data, like how spread out is the data? Because everyone in this room, to me, looks pretty much the same height, right? I think we're all pretty close to what, somewhere between 5 to 6 feet tall. I think everyone in this room is somewhere between 5 and 6 feet tall. It's pretty close to, right? But dogs, right? You get little tiny Chihuahuas, you get like Great Danes, you get dogs in the middle, like their heights are like super spread out, right? There's a huge distribution. There's a huge standard deviation in dog heights. So not only would I put the average dog height is less than the human height, right? But also their curve would be really wide, it'd be like really spread out. They would have a huge standard deviation. And I didn't put the formula for that up here, how to calculate this the sigma right here. It's called standard deviation, but there's a way to do it. And if you ever take statistics one day, then think about that, right? Think, okay, here's a way to measure how spread out that data is, right? Okay, right. So once you know statistics, you can statistics is really useful in all different branches of science to figure out lots of things experimentally. Like, is this drug like medically like valuable, or is it just placebo? Right? You could do all different. You can answer all kinds of questions with those. So let's look at like standard deviations from from the mean, right? So let's say you're running an experiment and you want to know, let's say I did some like theoretical work, and I think I've discovered like something that would deviate from the norm, whether it's some experimental drug, or in this case, the experimental particle is the story I'm going to link this to, right? So why it's on the screen right now, right? And you run some experiments. Now, let's say your experimental data shows like one standard deviation from the mean that you would expect with what's called a null hypothesis. So like if it was just placebo, or if it had no effect at all, right? Now that would show okay, that there was some kind of deviation from the mean, but like how reliable is that? Well, you might expect that to happen just randomly, like sometimes if it was really just like placebo or had no effect at all, right? So the further out on the tail that you can get, maybe by doing more and more trials, or if it's just like more effective, right, then the less likely that it would be completely random, right? Got more and better examples. So I'm really just trying to give you guys the crash course. I'm telling you guys like several months of stuff in like a few minutes here, right? And in particle physics, like all these collisions that they're running, you make like a bunch of different Feynman diagrams. This is a really simple one, right? For different particle collisions. They're looking at properties like mass, charge, and spin. And one analogy I've heard for discovering a new particle, like if you're like out to discover a new particle, we've done some theoretical work. We think there's a particle that looks like this. We're going to call it Higgs boson, right? And we think it has these properties. It's sort of like if you push a piano down a staircase, And you don't get to look at the piano, but you just get to hear the tinkling of the keys as it's like tumbling down the staircase. And then from that, you're supposed to reconstruct like, oh, here's what a piano would look like, so that it would create that tinkling of the keys as it's falling down the staircase. That's sort of what particle physics is like, right? We get these all these crazy random collisions, collect all this data about mass, spin, and charge. And then after like billions and billions of collisions, we can say, make a certain, you can come to certain determinations about like what lines up with theoretical physics. Right? And particle physics, there's what's called a 5 sigma particle discovery standard, 5 sigma standard. So if particle physicists say we've discovered a new particle, and the last one that was announced was, scroll back a few slides here, this guy right here, the Higgs boson. This was in 2012, so about 11 years ago. Okay. That is based on statistics, and it's because if the Higgs boson did not exist, then there would be about a 3 in 10 million chance that they would be seeing the data that they do. Right, so there you go. So there's your particle standard right there. Now, most branches of science have about approximately a 2 sigma standard. So if you like go into, I don't know, like medicine or economics or right anything else, a pretty traditional standard is, about 2 standard deviations. Right, but yeah, particle physics is really stringent, so they go with 5 standard deviations. Okay, right, and last slide I have for you guys. I think this one's just kind of interesting. Something called the fine structure constant. So this number designated with alpha, it shows up in certain places. I was trying to find out where this shows up. I think it has to do with like if you look at spectral lines, like certain ratios of things or certain ratios of like electron orbital shells or something. I don't know. It's kind of I was having trouble myself distinguishing exactly where this shows up. But this does have a certain physical applications, right? There's this number shows up about 1 in 137. And one thing that you'll notice if you're paying real close attention is you guys know that throughout this year, I've always said like no naked numbers, right? Like if you say the force is equal to 3 what? 3 pounds, 3 newtons, what are we talking about? Right? You have to label units, right? Right. The length is equal to 5. 5 what? 5 centimeters, meters, kilometers, what are we talking about? Right? This number has no units, right? Here's one way to get this number. There's other ways you can get it too, but let's see, we've got 2 pi times the electrostatic constant, think like Coulomb's law, the charge of an electron is here. Here's Planck's constant, showed you guys a few days back. Here's the speed of light, right? All the units cancel out, right? And you get this number that actually has physical properties and shows up. Right? Now, this number has no units. The only, when has there ever been no units in this class? I think when we were talking about like coefficient of friction, newtons over newtons, that cancels in a certain way. When else? There might be, okay, maybe like one every time ever, right? But here, right? So one cool thing I heard about this is that is true, right? Suppose we run into alien life one day, right? And we're communicating with each other, like we're technological, they're technological, we're comparing notes about, well, what have you discovered? What have you discovered, right? There are certain things we could communicate that we'd be able to communicate with each other, at least mathematically. Like, hey, we've discovered 3.14159. Oh, hey, we've discovered that. It's pi, right? Now, we might be using different bases, right? Maybe we're on a base 10 system for the most part, right? We also have base 2, like running in computers. Maybe aliens like base 12 or base 60 or base 8, right? But, you know, who knows? But some way or another, we'd be able to communicate, like mathematically, we've discovered different numbers, like, hey, 2.71828. Hey, we discovered that too, right? But what could you say you discovered in terms of physics? Like not in terms of pure math, but in terms of physics. Well, that'd be kind of hard. Like we could say, hey, we've discovered the universal gravity constant, but that has units attached to it. So if you say like, right, like 10 to the negative 11, right, Newton meter squared per kilogram squared. Well, now you have to explain like what is a Newton and a kilogram and a meter. And if you don't have those defined, then the rest of the number doesn't really matter, right? So you'd have to like define units first, right? Oh, we've discovered the speed of light, 3 times 10 to the 8 meters per second. Okay, great, but what is a meter and what is a second? Because without that, the number doesn't really mean anything. Right? But this number here is like a number that you could communicate to aliens, and they would have the exact same number, you know, like the same base, like base 10 or whatever, right? Right? Because all the units end up canceling out regardless of how you define the units in the first place. So anyway, that's kind of interesting. That's there. It's called fine structure constant. It's a complete mystery as to why this number is this number. There's speculation that, hey, maybe other universes have other fine structure constants that lead to complete other like laws of physics, like one or another. So all right, there you go. That's the last slide I got for you guys. So yeah, that's gonna wrap up. Yeah, I guess anything I have to tell you guys. So yeah, again, I hope you guys have learned a lot from this class and are able to make good use of it.